All right, welcome everyone. Let's dive right into this explainer and unlock the foundational rules of algebra that govern real numbers. Today, we're taking a highly structured journey through the absolute bedrock of mathematics. We're going to break down the properties of real numbers, and then we're going to directly apply them to completely conquer exercise 1.2 from our source material. Let's get started.
Before we even think about solving complex equations or mastering advanced algebra, we really have to understand the invisible rules operating behind the scenes every single time we add or multiply. Think of these properties as the source code of the math universe. Without them, numbers would just be chaotic, meaningless symbols. But with them, we get this perfectly balanced, beautifully logical system.
So, here is our game plan for today. We'll start with Section 1, Addition and Multiplication Properties, then Section 2, Equality and Inequality Rules, and finally, Sections 3 through 5 are all about applying those exact rules to crush Exercise 1.2.
Kicking things off with Section 1, Addition and Multiplication Properties.
Take a look at how the commutative and associative properties just beautifully mirror each other. Whether you're adding or multiplying, the commutative property basically says the order of the numbers doesn't change the result. Like 3 plus 7, exactly the same as 7 plus 3. The associative property takes this a step further. It tells us that how we group the numbers in parentheses also doesn't matter, which, trust me, is going to be crucial for part 2 of our upcoming exercise. You can calculate A plus B first, or B plus C first, and you will arrive at the exact same destination.
Now, what's actually really fascinating here is the sheer contrast between identities and inverses. An identity literally leaves your number completely alone. Adding 0, our additive identity, or multiplying by 1, our multiplicative identity, keeps your original number completely unchanged. Inverses, on the other hand, are designed to cancel your number out entirely. The additive inverse is just its opposite, right? Like positive 6 and negative 6, which combine to make 0. And the multiplicative inverse is its reciprocal, think 3 and 1/3, which multiply together to just leave you with 1.
Okay, moving on to the distributive property. Think of this one as your ultimate bridge. It connects our two main operations, allowing multiplication to sort of sweep across the addition or subtraction trapped inside your parentheses. So if A is multiplied by the group B plus C, A distributes to both of those terms, giving us AB plus AC. It is arguably the absolute most powerful tool for expanding equations that you're going to use in all of algebra.
All right, that brings us to Section 2, Equality and Inequality Rules.
When we're dealing with equations, we rely on 3 foundational properties of equality. Think of the reflexive property as literally looking at a mirror. A will always equal A. The symmetric property is more of a two-way street. If A equals B, well, then we can safely say B equals A. And finally, the transitive property is your stepping stone. If A equals B and B equals C, then we can easily bridge that gap and conclude that A absolutely must equal C.
Now, for inequalities, we've got the trichotomy property. Yeah, I know, big word, sounds kind of intimidating, right? But honestly, it's deeply logical. It just means that when you compare any two real numbers, let's call them A and B, there are literally only 3 possible relationships they can have. Either A is greater than B, A is less than B, or A is exactly equal to B. Only one of those can be true at any given time. Simple as that.
Inequalities also have additive and multiplicative properties. But watch out here, guys, because there is a massive trap you need to avoid. You can add the same number to both sides of an inequality, and the sign stays exactly the same. But the multiplicative property, that's the crucial one. If you multiply or divide an inequality by a negative number, you absolutely must flip the inequality sign. Like if A is less than B and you multiply both by -2, that new relationship is now greater than. Keep that strictly in mind.
Theory time is over. Let's jump right into Section 3, Exercise 1.2, Recognizing Properties. It is time to step into the arena. We're going to systematically conquer Exercise 1.2, starting with Question 1, which challenges us to figure out the specific property being used in 12 different equations.
Now, instead of doing these one by one and getting completely lost in the weeds, let's group our answers by the patterns we literally just learned. Look at parts 1, 4, 6, and 7 from the exercise. In all of these, the numbers are exactly the same on both sides, they've just swapped places. That means they're textbook examples of the commutative property. Part 2 shifts the parentheses around, making it our sole associative property example. Meanwhile, parts 3, 5, and 11, they brilliantly illustrate the distributive property in action. For example, in part 3, 9 is being multiplied by a group of fractions, and on the right side of the equation, you can see that the 9 has been successfully distributed to each fraction individually. Now, for the rest of question 1, we're dealing with identities and inverses. Notice how in part 9, they add positive 3/5 and negative 3/5, and the result is 0. That definitively proves it's the additive inverse property. On the other hand, parts 8, 10, and 12 multiply fractions by their exact reciprocals to achieve a result of 1. Take part 8, for instance. 2/11 multiplied by 11/2 equals 1. This makes them perfect examples of the multiplicative inverse property. Moving right along to Section 4, Exercise 1.2, fill in the blanks. For question 2, we are basically playing mathematical detectives. We just use our properties to balance the scales. In part 1, the left side has root 2 over 5 plus 3 over root 6. The right side already has the 3 over root 6, so to maintain the commutative property of addition, the missing box obviously must be root 2 over 5. Simple, right? In part 5, we have negative 21 plus a blank equals 0. By definition of the additive inverse, we need the exact opposite number, so the answer is positive 21. The rest of the parts, 2, 3, 4, and 6, follow this exact same mirror logic. You're simply swapping the order to maintain symmetry. Okay, questions 3 and 4 deal with inequalities. Question 3, part 1, says if 5 is less than 8 and 8 is less than 10, well then 5 absolutely must be less than 10. That's our transitive property shining through. And part 2 follows suit. But, and this is a big but, heads up for the traps in parts 3 and 4 of question 4. In part 3, we start with 6 being greater than 4. Cool. But then, both sides are multiplied by negative 7. And remember our rule? Because we are multiplying by a negative number, the inequality sign flips entirely. That greater than symbol becomes a less than symbol, making negative 42 less than negative 28. And finally, let's bring it home with Section 5, Exercise 1.2, Finding Inverses. This one is super satisfying. Remember this really simple set of rules for question 5? To find the additive inverse, you literally just flip the positive or negative sign. Boom. So for the number 3, the additive inverse is negative 3. For negative 7, it's positive 7. Easy. Now to find the multiplicative inverse, you just flip the number into a fraction. The multiplicative inverse of 3 becomes 1/3. Just follow this pattern for the remaining numbers in the exercise. But wait a second, pay special attention to the number 0 at the very end. Its additive inverse is just 0, but its multiplicative inverse? It doesn't actually have one. 1 divided by 0 literally breaks math, making it undefined. And just like that, we've successfully navigated the rules and applied them to completely conquer our source materials exercise. But you know, the real takeaway here is that the properties of real numbers aren't just some abstract rules you memorize for a test and forget tomorrow. No, they are the fundamental tools for solving every puzzle in algebra. Whether you're balancing a basic budget or eventually calculating a rocket's trajectory, these exact same properties, commutative, associative, distributive, and all those rules of equality, they hold absolutely true. When you look at math through the lens of these structured properties, what once looked like chaotic numbers randomly bouncing around becomes a highly predictable, totally understandable system. So that wraps up this explainer. Keep practicing these properties, refer back to the structured rules we went over today, and you'll quickly realize that no math problem is truly unsolvable. So, now that you know the invisible rules governing numbers, what complex equations are you going to break down next?